Something really quite strange from the quantum world. It challenges our everyday intuition about, well, just turning things.
Right.
Think about this. What happens when you rotate an object, say a coffee cup, 360 degrees?
Well, it comes right back to where it started. Looks exactly the
Yeah,
same.
that's just common sense, isn't it? But now, imagine a fundamental particle, like an electron. It needs a full 720-degree rotation to get back to its original state.
2 full turns.
2 full turns. It sounds bizarre. And this isn't just some mathematical quirk, right? It seems to point to something deeper about reality, something woven into space-time itself.
That's the idea, yeah. It's fundamental.
Okay, so we've looked at a bunch of sources, including bits from the topology of spin, a 720-degree quantum rotation, to try and unpack this. Our mission for you today is to help you understand why this weird quantum behavior isn't just real, but actually essential for, well, everything. So let's dig in. How can 360 degrees not be enough?
It's fascinating, really. The answer isn't just about the electron itself, but it's kind of hidden in the geometry and the topology, the sort of fundamental shape of rotation itself.
Okay, geometry and topology of rotation. That sounds like a good place to start. Because, yeah, to get this quantum stuff, we probably need a solid handle on just normal, everyday rotation first. So how do physicists, formalize rotation in our 3D world?
Well, fundamentally, a rotation is just a transformation, a way of moving something that keeps all the distances between points the same. And it also keeps the handedness, like a right hand stays a right hand after rotation.
Okay, so no stretching, no squashing, no mirror images, just turning.
Exactly, like
Okay.
turning a key in a lock. And all these possible rotations, they form what mathematicians call a group.
A group, right, meaning you combine rotations, you get another rotation, there's a do-nothing rotation, and you could always undo a rotation.
Precisely. And because you can smoothly change the angle or the axis, it's a special kind called a Lie group. It's continuous.
You mentioned it's also non-abelian. What does that mean in simple terms? Why is that important?
Non-abelian just means the order you do rotations in matters, which, we know from experience.
Right, like rotating your phone screen up, then sideways is different from rotating it sideways first, then screen up.
Exactly that. The final orientation depends on the sequence, and the formal name for this whole collection of 3D rotations is SO3, Special Orthogonal Group in 3 dimensions.
SO3. Got it. So that's the mathematical framework for something we do constantly. How do we describe one specific rotation within SO3?
Usually with an axis and an angle, rotate 90 degrees around the vertical axis. Simple enough.
Seems straightforward.
Mostly. But there's a little catch. A 180-degree rotation, a half turn, around some axis, let's call it n, looks exactly the same as a 180-degree rotation around the axis, pointing in the completely opposite direction, n.
Ah, okay. Turning something halfway around facing north is the same as turning it halfway around facing south.
Exactly, and that seemingly tiny detail, that's actually the seed. It's where the really interesting topology comes in.
So we're not just talking about doing rotations, but thinking about the space of all possible rotations. Can we actually picture this space, this SO3?
Yeah, there's a neat way to visualize it. Imagine a solid ball, like a bowling ball, with a radius of, let's say, pi radians, which is 180 degrees.
Okay, a bowl.
The direction from the center of the ball to any point inside tells you the axis of rotation.
Right.
And the distance from the center tells you the angle. From 0 at the center up to 180 degrees, or pi, right at the surface.
So the center's no rotation, and the surface is all the 180-degree rotations. Makes sense.
But here's where that 180-degree ambiguity bites, that n versus n thing.
Yeah.
It means that points on the surface of our ball, which are directly opposite each other, antipodal points, actually represent the same 180-degree rotation.
Whoa, okay. So the north pole of the ball is mathematically the same point in rotation space as the south pole, and every point on the surface is identified with the one opposite.
Exactly. You have to mentally glue these opposite points together. And that identification, that gluing, is what makes the space weird. It makes SO3 not simply connected.
Not simply connected. You used the donut analogy earlier, like a loop going around the hole can't shrink to a point.
Precisely. On a simple sphere, any loop can shrink. On a donut, some can't. In our SO3 ball with the glued surface, there are also loops you can't just shrink away.
So what does a normal 360-degree rotation look like as a path in this twisted ball space?
Okay, imagine starting at the center. no rotation. You move out along a radius, say, towards the North Pole until you hit the surface. That's a 180-degree rotation.
Right.
But because the North Pole is identified with the South Pole, your path effectively jumps instantaneously to the South Pole and continues back along that diameter to the center. That full trip, center to surface and back from the opposite side, represents a 360-degree rotation.
Ah, and that path going across the diameter like that is one of those loops that can't be shrunk down because the endpoints are glued together.
You got it. It's topologically non-trivial. It's stuck.
So what about 720 degrees then?
A 720 is like doing that diameter trip twice. Go out to the North Pole, pop back from the South Pole to the center, then do it again. Go out to the North Pole, pop back from the South Pole to the center.
It's two full traversals.
And that path, the double loop, can be shrunk down to a point in this space. It's topologically trivial. It's like you've untangled something.
Wow. Okay. That's still pretty abstract, but I know there's a fantastic way to sort of feel this difference, right? The Dirac bell trick.
Yes. Or the plate trick or the Balinese cup trick. It makes it really tangible.
Yeah, it's a great aha moment. So you hold the plate flat on your palm, arm out, keep your shoulders still. Or maybe use a belt, clamp one end.
Right, clamp one end, hold the buckle. The key is that your arm, or the belt, is tethered. It remembers how it's been twisted.
Okay, so now rotate your hand, holding the plate a full 360 degrees, keeping it level.
Your arm gets visibly twisted up, right?
Yeah, totally twisted. And the weird thing is, you can wiggle your hand around, move your elbow, whatever, but without actually rotating your hand back, you cannot get that twist out. It's stuck.
That twist is the physical manifestation of that non-shrinkable 360-degree loop in SO3. The tether remembers.
But then comes the magic part. From that twisted state, you do another 360-degree rotation with your hand, same direction. Total 720.
Now your arm looks even more like a pretzel.
It does. But then you can do this maneuver like passing your hand under your elbow or around.
And suddenly, miraculously,
The twist just vanishes. Your arm is completely untwisted, back to normal. And your hand hasn't actually changed its final orientation from the start.
Exactly. The 720-degree rotation corresponds to that shrinkable loop. The system can return to its initial state without any kinks.
So what's the big takeaway here? It's not about the plate or the belt, is it?
No, not at all. It's a fundamental property of orientations in 3D space. Anything connected to its surroundings, anything tethered, will exhibit this difference between one full turn and two full turns. And this is the perfect stepping stone into the quantum world. Dirac himself loved this analogy for spin.
Okay, so stepping into that quantum world, this hidden twistiness of rotation suddenly becomes like front and center.
Absolutely. It's not just a curiosity, it's foundational.
We talk about classical angular momentum things, orbiting or spinning. But quantum mechanics gave us spin, right? Intrinsic angular momentum.
That's right. And it's crucial to understand spin is not like a tiny billiard ball spinning. Electrons, for instance, are considered point particles. They don't have a physical size or axis in the classical sense.
So spin is just an inherent property.
Yeah.
Like charge or mass.
Exactly. It's just part of what the particle is. And it's quantized. It comes in specific amounts. Integer spin for particles like photons, the carriers of light, they're bosons. And half-integer spin for particles like electrons, protons, neutrons, the stuff matter is made of. They're fermions.
And we're focusing on these fermions, the spin 12 particles, because they're the ones with the 720-degree thing.
Precisely. Their spin is intimately tied to this peculiar rotational symmetry.
Okay, so how do we describe the state of these spin 12 particles? You mentioned spinors. What are they?
Spinors are the mathematical objects we use. Forget the 3D vectors of classical physics for a moment. Spinors are typically represented as two-component vectors, but the components are complex numbers, not real numbers.
Two complex numbers. Okay, already different.
Yes, it's a richer mathematical space. And this richer structure is what allows for the weird rotation property.
So what is that defining property? What happens when you rotate a spinor by 360 degrees?
Here's the kicker. When you perform a mathematical operation corresponding to a 360-degree physical rotation on a spinor, the spinor's mathematical representation gets multiplied by -1.
-1. So the state, let's call it C psi C, becomes minus C psi.
Exactly. It picks up a negative sign, a phase factor of -1. It's only after a second 360-degree rotation, making 720 total, that minus psi gets multiplied by -1 again, bringing it back to the original plus II plus check.
Okay, the flagpole analogy you mentioned. The pole turns 360, it's back. But the flag attached flips over.
That's a pretty good way to picture it, yeah. The spiner has this internal flag, this phase, that keeps track of rotations in a way classical vectors don't. It needs 2 turns for the flag to get back to its original orientation.
But hang on. This raises a big question, maybe for you listening too. In quantum mechanics, probabilities depend on the square of the state. And Tre is exactly the same as Cherry 2. So if the only difference is a minus sign, how could we ever possibly detect this? How do we know it's real?
Excellent question. You're right. If you just measure a single particle, you can't tell the difference between F and Tre. The probabilities are identical.
So
The key is interference. Quantum mechanics is all about adding probability amplitudes, not just probabilities. And when you add amplitudes, their relative phase matters enormously.
interference, like in the double-slit experiment, waves interfering.
Exactly like that. Imagine you split a beam of spin 12 particle, send one beam along a path, rotate it 360 degrees, and then recombine it with the unrotated beam.
Okay.
The rotated beam's amplitude is now mensch, while the unrotated one is plus. When they recombine, if they started out equal, you get plus, which equals 0, destructive interference. That minus sign makes a physically measurable difference. The particles might avoid going in a certain direction entirely.
Wow. Okay, so the minus sign isn't just math. It shows up in experiments where paths combine.
Absolutely. It's very real.
Now, you mentioned the math behind this involves SU2, not SO3. Let's bridge that gap. What is SU2?
Right. SO3 is great for classical rotations in 3D space, but the natural mathematical home for spinors and their rotations is SU2. It stands for Special Unitary Group in 2 dimensions.
Special unitary. What does that mean?
It means we're talking about 2x2 matrices with complex number entries. Unitary means they preserve the length of these complex vectors, which is crucial for keeping probabilities summing to 1 in quantum mechanics. Special means their determinant is +1, which is related to preserving orientation in a complex way.
Okay, 2x2 complex matrices with these properties. And you said the shape of this group, SU2, is different from SO3. It's like a 3-sphere.
That's right. Topologically, SU2 is equivalent to the surface of a sphere in 4 dimensions called SE2. It's hard to picture, I know.
Yeah, definitely.
But the crucial difference is this. Unlike SO3, which was twisted or not simply connected, SU2 is simply connected.
Meaning any loop you draw within the space of SU2 can be smoothly shrunk down to a single point. No stuck loops like in SO3.
Exactly. It doesn't have that fundamental topological obstruction that SO3 has. And this topological difference is really the ultimate source of the whole 720-degree phenomenon.
Okay, so SU2 is simply connected. SO3 isn't. How do they relate? You mentioned the double cover.
Yes, this is the core mathematical link. There's a mapping, a function, from SU2 onto SO3. It's a special kind called a homomorphism, and it's specifically a 2-to-1 mapping. Meaning, for every single rotation in our familiar SO3, there are 2 distinct matrices in SU2 that correspond to it. If you have a matrix U in SU2 that maps to a certain rotation in SO3, then the matrix FX-U also maps to that exact same SO3 rotation.
So SU2 kind of covers SO3 twice over. Like 2 sheets of paper lying exactly on top of each other, both mapping down to one map underneath.
That's a great way to put it. SU2 is the universal cover of SO3 because it's simply connected and it covers SO3.
So how does this finally explain the 720 degrees? Let's tie it all together.
Okay. A spinor state, remember, lives in the space of SU2, this simply connected 3-sphere.
Right.
Now, when you physically rotate the system by 360 degrees, that corresponds to tracing out that non-shrinkable loop in SO3 that we talked about, the one going across the diameter of a ball model.
Got it.
When we lift that path up into SU2, where the spinor actually feels it, that 360-degree physical rotation takes the spinor state from the starting point in SU2, represented by the identity matrix I, not back to I, but to the other matrix that corresponds to no rotation in SO3, which is II.
So a 360 turn in our world is only half a journey for the spinor in its own mathematical space.
Yeah.
It ends up at I instead of I.
Precisely. The spinor is now in the state taste. To complete a full closed loop in SU2 and get back to the starting point I, you have to continue the journey from I back to I.
And that continuation requires
another 360-degree physical rotation in SO3. That second 360 takes the state from I back to I in SU2.
So total 720 degrees physical rotation to make one closed, shrinkable loop in the spinor's natural space, SU2.
Exactly. That's why a spinor needs 720 degrees to return to its original state. It's the minimum rotation needed to trace a topologically trivial loop in SU2.
That's elegant, actually. Different spaces, different rules. SU2 for the spinors, 720 degrees. SO3 for classical vectors, 360 degrees. And SU2 double covers SO3.
It's a beautiful piece of mathematical physics. But crucially, it's not just math. It's been tested.
Right, the experiments. Where this really hits the pavement, neutron interferometry sounds like the key one.
Yes, neutrons are perfect. They have spin 12, so they're fermions and should show this effect, but they're electrically neutral, so you can manipulate their spin with magnetic fields without worrying too much about electrical interference messing things up.
So how does the experiment work, basically?
You take a beam of neutrons, and using a perfect silicon crystal, you split the beam into two separate coherent paths, like the quantum version of a beam splitter for light.
Okay, two paths.
One path goes straight, acting as a reference. The other path goes through a region with a carefully controlled magnetic field. This field makes the neutron spin rotate, like a tiny spinning top precessing. You can precisely control the angle of rotation.
By adjusting the magnetic field strength, or the time the neutron spends in it.
Exactly. Then you use another part of the crystal to recombine the two paths, and you put a detector there to see how many neutrons arrive.
And you're looking for interference effects based on the spin rotation. What was the verdict?
Absolutely unambiguous. When the magnetic field was tuned to cause exactly a 360-degree rotation of the neutron spin along one path, the detector measured destructive interference. Fewer neutrons arrived than you'd expect by just adding the beams. This was direct proof of that Nino-1 phase factor. The n-tum canceled out.
Wow, and for 720 degrees?
When they tuned the field for a full 720-degree rotation, they saw constructive interference. The detector signal was strong. The state returned to plus base, interfering positively with the reference beam.
So, direct physical confirmation. The spinors really do flip sign at 360 and come back at 720.
Irrefutable proof. It's one of the classic experiments demonstrating the reality of spinor phases.
And this difference, this 360 versus 720 symmetry, it's not just some weird isolated effect, is it? It connects to something much bigger.
Oh, much bigger. It's absolutely fundamental to the structure of matter. It relates to how we classify all particles in the universe.
You mentioned indistinguishable particles earlier. In quantum mechanics, if you have two identical particles, like two electrons, you can't tell them apart. Swapping them shouldn't change anything physically observable.
Right. But mathematically, when you swap them, their combined wave function can do one of two things. It can either stay exactly the same, symmetric wave function, or it can pick up an overall minus sign, antisymmetric wave function.
Okay, symmetric or antisymmetric, where does spin come in?
This leads directly to the spin statistics theorem. It's a really deep result connecting a particle spin, its rotational properties, to its behavior when swapped with an identical particle, its statistics.
And the theorem says?
It says particles with integer spin, like photons, spin 0, 1, 2. The ones with 360-degree symmetry must have symmetric wave functions. They're called bosons.
Okay.
And particles with half-integer spin, like electrons, protons, neutrons, spin 1232. The ones with 720-degree symmetry must have antisymmetric wave functions. They're called fermions.
So that 720-degree rotation property is the defining signature of a fermion.
It is. It dictates their fundamental exchange behavior.
And this anti-symmetry for fermions, that leads somewhere incredibly important, doesn't it? The Pauli exclusion principle.
Directly. Think about what antisymmetry means. If you tried to put two identical fermions, say two electrons with the same spin orientation, into the exact same quantum state, then swapping them would have to flip the sign of the wave function. But swapping them should also leave the state unchanged, because they're in the same state. The only way a number can be equal to its negative is if that number is 0. So the wave function for such a state must be 0.
Meaning zero probability finding them in that state.
Exactly. Which means no two identical fermions can occupy the same quantum state simultaneously. That is the Pauli exclusion principle.
And this principle, born from the 720-degree symmetry and the resulting antisymmetry, this is the big so what. This is why the universe has structure.
Absolutely. This is arguably one of the most important consequences. If electrons were bosons, not fermions, they could all just pile into the lowest energy state around an atom's nucleus.
A tiny, dense blob.
Pretty much. But because they are fermions, they obey Pauli exclusion. They have to stack up into different energy levels, different orbitals, creating the electron shell structure.
Which gives atoms their size, their shape.
And dictates all of chemistry. The way electrons arrange themselves determines how atoms bond, forming molecules, leading to the incredible diversity of materials we see.
It also gives matter its stability. Right. It prevents everything from just collapsing in on itself.
Yes, it creates an effective degeneracy pressure. It's what gives solids their rigidity and liquids their volume.
Yeah.
Without the Pauli principle stemming from that 720-degree fermion nature, matter as we know, it couldn't exist.
So no stars burning stably, no planets, no tables, no us, just mush.
It would be a very different and likely much less interesting universe. The 720-degree twist is fundamental to existence itself.
Okay, let's recap for everyone. We started with this really weird idea. Quantum particles needing 2 full turns, 720 degrees to get back home.
Yeah, seems crazy at first.
We saw how even classical rotations have this hidden topological twist, revealed by things like the Dirac belt trick, that 360 degrees leaves a persistent twist, but 720 undoes it.
Right, the property of SO3 being non-simply connected.
Then we met quantum spin and spinors, these complex mathematical objects that actually do pick up a minus sign after 360 degrees.
Living in the space described by SU2.
And we saw SU2 as the simply connected double cover of SO3, meaning our 360-degree rotation is only half the journey for a spinor. It needs 720 to complete a loop in SU2.
The math ties it all together.
And crucially, experiments like neutron interferometry proved that minus sign is real, showing up as interference.
Undeniable evidence.
Which then led us to the spin statistics theorem, 720-degree symmetry means fermion, which means antisymmetric wave function, which means the Pauli exclusion principle.
Which means structure, chemistry, stability, the world around us.
So the final answer for you, why 720 degrees? Because a quantum particle like an electron isn't just a tiny spinning ball. Its state is described by a spinor, living in this richer mathematical space SU2. Our normal 360-degree turn only takes it halfway around a fundamental loop in that space. It needs the second 360, making 720 total, to truly return to its starting point, mathematically and physically.
It's a consequence of the deep underlying geometry of quantum reality.
So this property, this spinor nature, isn't just some random quirk. It's baked into the fabric of a relativistic universe. This fundamental twist divides particles into bosons and fermions, and it's the 720-degree nature of fermions that allows matter, atoms, chemistry, everything solid and structured to exist. It really makes you wonder, doesn't it? What other hidden topological features, what other twists in the rules might be shaping our reality in ways we haven't even begun to grasp yet?